Welcome to section 2 of chapter 1, predicate and functional propositions and quantifiers. In this section, we will explore predicate logic and important extensions of propositional logic that enable us to express and analyze mathematical statements involving variables. While propositional logic treats entire statement as simply true or false, predicate logic allows us to examine the internal structures of statements and describe properties and relationships among objects. This makes predicate logic a powerful tool in mathematics, computer science, and logical reasoning. We begin by examining predicate or functional propositions. A predicate represents a properties or relationships that apply to individual or objects, while a variable represents an element from a specified set of objects. For example, in the statement X is a teacher, the phrase is a teacher is the predicate and X is the variable. Unlike ordinary propositions, which have definite truth values, predicate statement contains variables and do not become true or false until values are assigned to those variables, because these logical predicates are the so-called open propositions. Open proposition is a proposition which contains at least one variable and its truth value is depending on the value assigned for that variables, so that it is an open, it is true or false after the value is assigned for the given variables. Next, we will discuss open proposition, also known as propositional functions. As I said, an open proposition is a statement that contains one or more variables and its truth value depends on the value assigned to those variables. For instance, the statement x minus 2 equals 7 can be represented by p of x. Because it is an open proposition expressed by the variable x. The statement remains open until a value is assigned to x. Once a specific value is substituted, the open proposition becomes a proposition with a definite truth value. The set of all possible values that may be assigned to a variable is called the universal set. The section also explains how open proposition can be transformed into propositions. One method is the substituting specific values from the universal set. Another method is by using quantifiers, which allows us to make statement about all elements or some elements of a set without specifying individual values. We will also introduce the concept of equivalent open proposition and examine situation in which an open proposition is always true for every element in the universal set. Another important topic is quantifiers. Quantifiers are symbols that convert open proposition into complete propositions. There are two main types of quantifiers. The first is universal quantifiers and existential quantifiers. Sometimes we call it existential quantifier. The universal quantifiers represented by the symbols which will be displayed in this digital platform means for all, for every, for each are some of the phrases that can be expressed the quantifier, universal quantifiers. A statement such as, by using these symbols, For all x, P of x is true, indicate that every element in the universal set possesses the properties described by P. The existential or the existence quantifiers represented by the symbols as displayed on the screen, you can see, means they exist for some or for at least for a few and the likes. A statement such as there exists x, P of x is true, indicating that there is at least one element in the universal set that satisfies the properties of this P. We will also examine the relationship between the universal and the existential quantifiers through negation. The negation of the universally quantified statement can be expressed using the existential quantifiers, while the negations of the existentially quantified statement can be expressed using the universal quantifiers. Understanding this relationship is essential for constructing logical argument and providing mathematical statements. Furthermore, we will study compound proposition containing quantifiers, just as ordinary propositions can be combined using logical connectives such as and or, and the others. Quantified proposition can also be combined to form more complex logical expressions. These sessions highlights how quantifiers interact with logical operators and how these interactions affect the meaning of the statement. Finally, we will consider combinations of the quantifiers. In many mathematical statements, universal and existential quantifiers appear together. The order in which these quantifiers occur is extremely important because changing their order can completely alter the meaning and the truth of the statement. Understanding these combinations is a key step toward mastering formal logical reasoning. By the end of this session, you will be able to define predicate and functional propositions, identifying open propositions in the universal set, explaining the roles of the universal and existential quantifiers, or what we call existence quantifiers, describes the relationships between the quantifiers and negation, analyze compound propositions containing quantifiers, and interpret the statement involving combinations of these quantifiers. In the next chapter, we will continue developing our understanding of the logical reasoning by applying these concepts to more complex logical expression and the mathematical argument. See you in the next chapter.